Good afternoon, everyone, and welcome to Algorithms and Data Structures. So in the last lecture, we finished recurrence relations and saw the master theorem as a unifying method for solving a certain type of recurrence relations, the ones that follow this pattern where T of n is a factor A times T of n divided by a factor B plus another term. And we saw that this master theorem is super helpful. So straightforward approach to solving our recurrence relations and getting the complexity of the algorithm that would be described by the recurrence relation. And we saw there are three cases depending on how they work for splitting, recombining, and their work in the leaves in the subproblems relates. And we looked at a couple of examples to study the master theorem, and we saw it's straightforward once you know the rules, but it's not a lot of manual work anymore when you try to manually solve the recurrence relation. Then we looked at dynamic programming, which helps us here to speed up recursive problems, avoiding to recompute and recompute subproblems that we had actually computed already. We saw there's a top-down approach as well as a bottom-up approach. And obviously, dynamic programming is a much bigger topic in the field of optimization, which relates to operations research. But here we looked at this from a recursive perspective and saw how we can massively speed up recursive problems. Then we looked into sorting. We saw very simple sorting algorithms like bubble sort and studied its complexity. We briefly looked at stability of sorting algorithms. And then we studied merge sort and quicksort, two highly efficient sorting algorithms in greater detail and see how they work. We saw there are lots of variations and lots of other sorting algorithms like heap sort. Maybe you watched this video of Obama when he visited Google and was interviewed there. I can highly recommend the video. And we saw that when we do comparison-based sorting, we are unable to be better than n log n. So n log n is a lower boundary of comparison-based sorting. There are exceptions, things like bucket sort, but those make some strong assumptions and specific circumstances. Feel free to look into bucket sort more if you wish. But typically, for most problems, you'd be using comparison-based sorting, and there n log n is your lower boundary. We saw bubble sort can actually be helpful for a few selected problems, not for all, but for some. Bubble sort is actually being used, which a lot of people probably don't think once they study bubble sort. And we saw in Python, we use timsort. And we also saw how we can do sorting in Python and use parameters to customize the sorting or apply sorting to other objects like tuples, whatever. So in order to do sorting, we also looked into recursion. And today we will go ahead with trees. Trees are a new data structure that we will study. It's eventually a graph with more constraints. We will look at different types of trees. We start with binary trees. We will look at so-called balanced search trees, and we will see how we can traverse a tree. And then we will actually have an application to machine learning. Since many of you study AI and you will learn more AI algorithms or machine learning algorithms in your subsequent courses, we will see that the stuff we're doing today with trees can then be done or can be used in order to do machine learning as well. So those are the decision trees, but this is something we will probably only do in the next lecture. So what is a tree? A tree is a recursive data structure. We've studied recursion before, so it was quite helpful to study recursion before looking into trees because trees assume that you know how recursion works. So a tree is a recursive data structure and it stores elements in a hierarchy and it has a couple of properties. So at the very top of a tree, you have the root. So the trees we look at and we say the top is the root. It's just the opposite, like a real tree in nature. You would have the root at the bottom. And but the way we visualize the trees, typically we put the root at the very top. And then we have a top node that is the root. And then a root has multiple children, can have maybe 0 children, 1 child, or multiple children. And each of that child only has 1 parent. We will soon start to visualize trees and see this. So a node can have multiple children, but every node has exactly 1 parent. And each node may contain some data. It can be integers, can be more complex objects, whatever. And this would be a very simple tree that just illustrates an organization chart of a company. So we have a company, and this company has multiple departments. So this is the root, the company, and we have multiple children, which is the R&D department, sales department, purchasing department, and manufacturing department. And as you see, each of these nodes has exactly 1 parent, which is the root. But these children, they may have more children or not. So we see purchasing does not have children, so no sub-departments, but manufacturing has, for example, 3 sub-departments, which are then children of the manufacturing node. And the value that is stored in these nodes here would be just that string. But we can store other values in the nodes as well. Then what are trees useful for? So whenever you use a computer and you deal with files and directories, you're in fact dealing with a tree because your file system is represented in some type of tree because you have directories and you have store files in the directories, but the directory has maybe subdirectories. So this is represented as a tree. When you do object-oriented programming, you work with inheritance, so you have classes that inherit from other classes. Eventually, you have also an inheritance tree because you have subclasses which are then children of the superclass. We've looked into exceptions in this course, and we saw how we can build our own exception classes and how we can raise exceptions. Eventually, there is a superclass, and then we have more concrete exception classes. So these are children of the superclass. So the exception trees, exception hierarchies, or the hierarchy of exception classes is eventually also a tree. Then we will have so-called search trees. So search trees are a data structure in which we store data in a tree so we can search it very efficiently. That's something we will study today. You all use database systems, and in your next semester, in your 3rd semester, you will also have a database course, and you will learn how to build build databases, how to use a database management system, how to do queries and read and manipulate the data in your databases. And internally, in the database management system, somehow you need to store these tables, say if it's about a relational database management system. And that's something that is typically represented as a special type of tree internally in your database management system, because these trees that are used in there allow us to query and manipulate data very efficiently. We also have decision trees, so you make decisions based on some properties, and you go down the tree, and eventually you will make decisions. Decision trees are something that I mentioned in the opening today, and it's something we will discuss in probably the next lecture. Today, we will look at some initial trees. And something you would also see is that trees are often a foundation for more complex data structures. Now, we've introduced this concept of an abstract data type a few weeks ago. And now we will introduce this concept for a tree, and then we will see how we can implement it. So we'll write lots of code today, and we see how we can actually implement that kind of data structure. For the abstract data type for a tree, something that literature often uses is a so-called position. That's a term that you could see as a synonym for a node in the tree, but in fact, the position in the abstract data type is more like of an abstraction of a node. And an element is stored at each position, or for now, just see position as a node. So we store some concrete value at a position, and a position satisfies this parent-children relationship I mentioned before. So a parent or a node can have 0 or multiple, or 1 or multiple children, but each child can exactly have one parent. And then we can have for each position, we can say a position is called P, and that one has a method that is called element. And element would return us the element or the value that is actually stored at that position P, where a position you could just see as a node. And then our tree is actually made of multiple nodes or positions. So we have a tree T, and that one has multiple methods for accessing, for reading. For example, we have a tree T, and we want to know its root. And so we call root as a method on the tree object, and what we get is actually the position or the node of the tree that is the root, so the top one from which the whole tree starts. You can also check, say you have some tree object and you have some position P, you could check whether P is actually the root of T, and that function would return true if that position P is the root of the tree T. And for a given tree T, maybe you want to know the parent of a position P. So what that method would return you is the parent position of P within the tree, or simply none if a position has no parent, and that would only be the case for the root. So the root is the only node or only position that does not have parents, because it all starts from the root. And there are a couple of more methods we can use to read from the tree. For example, if we have a tree T and we have the position that is part of the tree, we want to know the number of children that a position P or a node has. So the number of positions would be returned that are, and for which this number is the number of children positions of P. You could also check what are these concrete children of P. So you want to know that you have the position P in the tree T, and you want to know the children of P. So what this would return you is actually an iteration over the children of T. So we use a term here, we generate an iteration. This is some term we will investigate later in the lecture, and we will see what generation and iteration mean. But for now, you can just imagine this would return us the children of a position P. And then there's a little bit of more methodology, like we have this tree here, and you see there are some nodes or positions that do not have children. For example, purchasing has no children, or tuna, or Africa. And these nodes or positions that do not have children, they are called leaves. So they're the leaves. You can also imagine this in a tree. The tree starts with a root and keeps growing. You have more branches, but eventually you have leaves, which are the end of the tree, and nothing grows out of them. So we call the nodes that do not have children the leaves. So we can check if actually a position P is a leaf in the tree or not, and would return true or false. We could also get the length of the tree, which returns the number of positions that are in total in the tree. So not just the children of the root, but the overall number of positions. And we can also try to generate an iteration over the positions of the tree, as well as we can try to generate an iteration over all elements of the tree. So this is a difference because if we generate an iteration of all the positions, that would be the nodes. But if we generate an iteration of all the elements of the tree, this would be the concrete values stored at the positions or nodes. So that's a big difference. And we could also check if the tree is empty. That means if the tree does not have any positions or nodes. So these are some initial methods for a tree. And we will try to implement some of this, and we will soon start building our own tree and see how this would work. I've told you many times that I really like the Goodrich book because the Goodrich book provides a lot of code examples and how to build efficient algorithms and data structures. It's something really cool. However, I don't use the code examples from the book for this chapter here in the course because the book is very good, but it provides excellent but highly generic abstract data type definitions and implementations. So if you look into the Goodrich book, into the trees chapter, the code is extremely lengthy because it's done in a highly generic way, which is interesting because then you can have more concrete tree classes, but it just gets out of control. It's way too much code and something I don't like because I prefer short and simple code examples in this course. So we're not using in this chapter the code examples from the Goodrich book. Instead, we'll use our own examples. And we will now start implementing probably one of the simplest types of trees, concretely a binary tree. And the binary tree is a tree for which a node has 0, 1, or 2 children. So 2 children at the very most per node. And what we can do then is, so we have these nodes, and in the nodes, we are storing concrete element or a concrete value. And then each node has 0, 1, or 2 children. And we can put an order in there, and we can say we have a left child and a right child in our node. And when we try to put in some order in the nodes, we would say the left child comes first and then the right child. So imagine you want to store some values in a tree. Imagine you have a node with the value 5, an integer. And now you want to put in order and you want to add a value 2, then 2 would be the left child as a node. And if you add, for example, 8, 8 would be the right child of our node. So 5 would be the value in the node, and 2 would be the value in the left child node, and say 8 or whatever would be the value in the right child node. So we bring in some order like this. And obviously, there are some nodes that have 0 children, they are leaves, and there are some nodes that may only have 1 child. And these binary trees, they are simple, but in fact, they are probably the most frequently used types of trees, and we will start implementing them now. And once we have done this, we will actually run the code and we will see what these binary trees are useful for, because we can store values in these binary trees, and then we can query very efficiently and try to find values. So a tree helps us to organize data, and if we do it right, it will help us to be able to search or even manipulate the data very efficiently. And later we will compare this to other approaches like lists and binary search and so forth. But we will first start with implementing trees. You can use trees also for other things. For example, if you build a compiler, so a compiler would turn your source code into some executable format. You have different stages in a compiler. For example, Alexa would create you the token. So Alexa would look into your code and determine if one element is, for example, maybe a variable name, one is an identifier, like a variable name, or if it's a keyword or a literal. That's what Alexa would do. But next, you have to put these tokens into, you need to check if these tokens actually match a grammar. So if you're using the grammar of the programming language correctly. And something like this would then be done in a parser, in a compiler. And this parser would also create essentially a tree of your code. So imagine you write some code where you have a mathematical expression. And this can be represented as a tree. So imagine we are adding 3 and 1. So we have a binary tree where we have this node, it's an operation, it's a plus, and in the leaves we have concrete integers. So we have an addition of 3 plus 1. And the result, which is 4, gets multiplied by 3. And that result, so 4 times 3, which is 12, gets divided by this one here. And what this means is I am subtracting 9 minus 5, which is 4, and I'm adding 2 on top, which is then 6. And this over here was 12, and I'm dividing 12 by 6, because I have the division here. And I'm subtracting something from that result. So with such a tree, we can express mathematical operations in the right order. So we don't need to put parentheses here, but rather depending on how we build a tree. And something like this is also done in a compiler, in the parser, which checks eventually if your tokens match a grammar and you're following the grammar or the language correctly or not. So this would be one stage in a compiler. And for this, you would also have such trees. And here we're using a binary tree to express a mathematical operation. So feel free to try at home to evaluate this tree or even write code for it. It isn't that difficult in order to evaluate this here. And we can do this very well with a binary tree. Remember, this is the left child and this is the right child. For an addition, it does not matter if you mix up left and right, but for a subtraction or division, it does matter. Now, I'll show you how to implement a binary tree, and we will run it, and then we will actually study it and see what it's useful for. So, our tree will be composed of nodes. So we have a class node, and we need to be able to instantiate a node. So we need our initializer, and we have a concrete data value that we are storing in the node. So we say self.data is the data, but we need to do a little bit more because our node will also have a left and a right child. So we say self.left is none and self.right is none, because initially when we create a node, it has no left or right child yet, but we need to put in a concrete entry, concrete data. Now, I will try to add something into the tree. I've told you before, we want to bring in order. So I have a node that contains a value, say 5. And I want to, and 5 would be the root of my tree. And I want to add now a value 2. Because my node that has value 5 is the root, I already have a tree. And therefore, I have a node, which is the root. And now I need to add a new node and place it as the left child of the root, because 2 is less than 5. And we will try to implement this now with an insert method. So I want to insert a data into a tree. So the tree would always be represented from now on as an object of the node class, which has a value. And that would be the root. And I'm working with the root node to enter something. We will try this now. We can check if there is data in our root node. If there is data, I'm unable to put the data into the root node. if there is no data in the root node, but the root node is empty, because I passed, for example, a none value, so I only have a root node with no entry, then I can just put the data in the root node, because the data is none. There's no data in the root node. I just put the data there. But if there is data in the root node, I need to check if I need to go to left or right. And what I can check is my data that I want to store in the tree. I want to check if it's less than the data that is stored in the root node. And if it's less, I can do something. It could be a different case that, for example, the data is greater than the data in my root node. For now, I only want to store unique values in it, so I can only add a value that is less than my data or greater than. I want to ignore duplicate values for now, at least in this very initial tree. So what I can try now is my data is that I want to add is less than the value in the root node. So I need to go to the left. And what I could do is I could say, I'm creating a new node with my data and I'm storing it in the left. So self.left refers to the left attribute of my node. And I'm storing in there a reference to a new node object that contains the data. This would be also something we can do for the right. We can say self.right has a new node also with the data if the data is greater than the value in my node. Are you okay with this up to here? Maybe just confirm, thumbs up, thumbs down, or if you have any questions, if this makes sense. Are you okay with the implementation, or do you think it can be improved? Do you see something that works or something that may not work if I want to add a lot of values? If you have any comments, turn on your mic or tell us in the chat what you think works or what may not work. If you think it works, maybe green reaction. If you think there is some issue in it, maybe a red reaction. So if we got a red one, but it disappeared, a green one. Someone has sent a red one which disappeared. Maybe just turn on your mic and tell us what you think may not work. Well, then answer. There's a very good answer. What if left and right already have elements in them? Yes, I would be overwriting them because there is maybe already something in left or right, but we're just overwriting it. So I don't want to do that. So I actually need to check if left is none. And if left is none, then I can do this. But if there is something stored in left already, then I need to take advantage of this recursive data structure because there is something in the left node already. That means I cannot store in the left node, but I can go into the left node and decide whether I need to store left or right in this left child node. So here I'm taking advantage of recursion. So I say self.left, this is now the node I want to look at, and I want to insert my data into the left node. And this is the recursive call. So I say self.left, I'm looking at the left node, and I want to insert, and then this is called recursively, and then I'm storing the data in the left node. And there, again, in the recursive call, it is checked whether the data is less or greater than the data in that left node. So it's a recursive call, and I'm building a recursive structure like this. Now I'm doing exactly the same for the write node. I'm checking if self.write is none. If it's none, I'm creating a new node. Otherwise, I'm doing exactly the same. I say self.write.insert the data. Are you all okay with this? If you're not okay, let me know and we can discuss it. But looks okay. So now we've started the first thing. We're able to add something into the tree. Next, we want to be able to find if a value is in the tree or not. So we can also implement find value. I want to search a value in the tree. And I would call find value on the root node, and it would check then if the value is in the node or not. If the value is in the tree or not. We would check, is value less than the data? We have one thing. We can check if the value is in the data. If the value is greater than the data, or we have some other case. So let's try to take advantage of this structure. What we could do is we can check if the left node is none. And if value would be less than the data, but there is nothing in the left, then that value cannot exist in the tree, because if value is less than my root node value, but there is no left child, then there's obviously no value like this in the tree. If the left reference is not none, then I'm doing a recursive call, and I'm saying self.left.findVal, check if this value is in the left subtree. So this is a node, and we have the recursive call then find value of our value. We're doing exactly the same for looking into the right child. We check if the right is none, but the value would be in the right side of the tree, but there is nothing in the right, then I return false. Otherwise, I'm checking self.write, find value, and I'm having the same recursive approach. And then we just keep it simple, and for the else, we say we return true. It's just the beginning. And we will start to evaluate this now, and I'll show you how. So we have our node class, and we can say root. Root is a node with value 5. And so far, root has nothing in its left or right. All what it has is the data which is stored in the root node. So we can search value 5, which is in, but value 4 is not in, and value 8 is also not in. Let's add it. So we can say an insert, we can say we insert a 2, and we insert a 9. Now what I see is root.left has now a reference to an object. So what this means in the interactive mode is I have some reference to something in the memory. And we can try to read out the data in there. And we see we have a 2 stored in the left now. And so we have a 9 stored in the right. Now I'm asking you, I want to insert a 10. Where would this 10 be stored? Inserting it. And I want you to either turn on your mic or tell me in the chat where you think the 10 would be stored in this tree now. We can already search it. It's definitely in, so the 10 was added. And I want to see, one person says the right child of 9. And that's correct. So root.right was the 9, but this one has a right child. We see there's a right child. There's no left child of the right child, but the right child has a right child, and we can check the data, and we see there's a 10 in there. So this overall, I think, looks interesting. We're able to store and read from the tree. But we've just looked into these references and checked, is there something in the left or right or not? There's not really like a structured process how we can go through the tree. Ideally, I would like to read out everything that is in the tree. And for this, we need a new concept, which is called traversal. And I'll show you this. So traversing a tree means going through the tree. So it's a process of visiting each node in a tree data structure exactly once. So we want to go through all the elements in the tree in some way. And there are different tree traversal algorithms. And we will check this now, which algorithms are available. And we will look at an example and try to understand how these tree traversal algorithms work. And then we will implement them. There are overall 4 main traversal algorithms. I'll mention their names first, and we will soon visualize them. There is an in-order, a pre-order, and a post-order. You'll see in 2 minutes what in-order, pre-order, and post-order mean. They are all very, very similar, and they are so-called depth-first methods. And there is another tree traversal, which is called level order, which works totally different, and that's a so-called breadth-first approach. These terms, depth first and breadth first, these are terms that are sometimes discussed in detail if you take a whole lecture or class on graph algorithms, because they are actually depth first and breadth first are more generic algorithms for graphs, not just for trees. But in this lecture, we are discussing depth first and breadth first from a tree perspective. And we will actually focus on in-order, pre-order, post-order, and level order. So we will not really use the terms depth first and breadth first anymore in today's lecture. And we see these 3 are very much related, and level order is a little bit different. And I'll show you now how to use or what these terms mean, how we can traverse a tree, and then we will see how to implement this. For this, I'm switching to the whiteboard. So I will show you an example tree, and we will do tree traversal. And we have a tree, we have different nodes, and I'm first drawing the tree. I also have this tree in the slides, and then I'm putting in concrete values into the nodes. So what we see here is we have a root node, and this one has a value f. And the root node f has a left child where we have values b and a right child g. The right child g only has a right child that has value I, and that node only has a left child that has a value h. And for our b has a left child, which is a, and a right child, which is d, and d has a left child, which is c, and d has a right child, which is e. So what we see is we have A, B, C, D, E, F, G, H, I stored in this tree and ordered correctly, because we see that B is less than F, G is greater than F, A is less than B, D is greater than B, and so forth. What you see is we have a few more elements in the left subtree and less, so we have more elements here and less there. This has to do with how we add the elements to the tree, but this is something we'll discuss later. For now, we just assume that the tree looks this way, and we will look now at different traversal methods. The probably simplest one is the level order. And we are starting now with level order. Level order means we are starting with the top level of the root of the tree, which would be just the root, and take that value first. So we print out that first, which is f. Then we go into the next level and read out from left to right. So it would be b and g. How would the level order continue if I look into the third level and fourth level? Maybe you can write me in the chat how level order would be continuing, that we go into the next level and read out from left to right in the whole tree. So we have A, D, and I, that's correct. And how does it continue? C, E, and H. First level, second level, third level, fourth level. I'm just deleting those red ones because we'll do more traversal. So the level order is probably the simplest tree traversal. And we will continue now with in order, pre-order, and post-order. And I'll explain you what they mean. So we'll do in order first. In order, and the first time you see this, it will be a bit confusing and you will probably mix up in order, pre-order, post-order, but you need to practice this and we will implement it and turn it into code. And then you see it actually looks more complicated than it is. With in order, I'm starting at the root and I'm checking if there is a left child. If there is a left child, I'm going to the left child, which would be B. I'm not printing out yet. I'm just exploring. I'm going through, but not printing it. The left child is B. B has a left child, so I'm looking at A. And A has no left child, so I'm done going left, and I'm printing out value A. And then I want to do the same procedure with the right subtree of A. But A has no children. So I'm done with this A leaf because A has no left child and no right child. And the order is go left. If you cannot go left anymore, print out the value where you are right now, and then do the same procedure with the right. So A has been done and we're done. Now we go back in the recursion tree to B, because we were at B before looking at A. And B will be printed out now because we have finished exploring the left subtree of B. We are printing out B, and then we are doing the same procedure for the right subtree. I'm looking into D, not printing yet, but I'm looking then from D into its left subchild, which is C. And C has no left child, so I'm printing C. There's no right subchild or no right child of C. So I'm done with C. I'm going back to D because the left has been explored. I'm printing out value D. And then I'm doing the same procedure for E. I'm looking into E. There's no left child. I'm printing out E. And there is nothing in the right of E. So I'm printing out E. Now I'm done with this whole subtree here, which was the subtree of F. Which value would I be printing out next now within order? Tell me in the chat, because I've looked at the whole subtree of F. So I'm printing out F. And now I'm continuing this with the right child. So I'm looking into G, but G has no left child. So I'm printing out G. And then I'm looking into the child, the right child of G, which is I. I has a left child. H, I'm looking into H. There's no left child of H. I'm printing out H. There's no right child of H. So I'm going back to I. I'm printing out I. There's no subchild, and I'm going back to recursion, and I'm done. So within order, we can print this out in exactly the right sorted order. There are two more, which is pre-order and post-order. Pre-order almost works. So in order, pre-order, and post-order, so post-order will also come later, they're all very similar. They just do a few steps slightly different. With pre-order, I'm printing out the value in the node first, which is F. Then I'm going into the left subtree, which is element B, and I'm printing out B. Then I'm looking into the left child of B, which is A. I am printing this first, but there is no left child and no right child to continue in A. So I'm going back to B, and I'm continuing this process for the right subtree of B. So which value would I print out next after I have finished looking into the left child of B, and I'm continuing this process for the right subtree of B? What would I be printing next? D, that's correct. What would be printed after D? Exactly C, and then E, that's correct. And then I have done the left subtree of F, and what would come next when I look at the right subtree? Correct, it's G, I, and H. So you understood that concept well. Now, post-order is again, so in order means first going left, then printing, then going right. Pre-order means printing first, then go left, then go right. And post-order would mean first go left, then go right, and then print my node value. So what if I apply post-order to my tree? Which one would be the last node I'm printing, or which would be the last value I'm printing? The very last one. So I'm doing post-order on this whole tree. What would be the last one? That's correct, it's F. F would be the very last one, because I'm first looking into the left subtree, then the right subtree, and then I'm printing the value. Now, F would obviously be the last value because it's the root value. Now, what would be the first value I'm printing if I'm looking into post order? I go to the left, which is B, which has a left, which is A, but there's no left and right to look into A, so A would be printed first. Then I'm looking into the right child of B, which is D, but D still has a left child, which has no children, so C has no left or right children, so I'm printing C. Then I'm looking into the right child of D, which is E, which has no children, so I'm printing this. And then I'm printing values D, and then B. And how does this continue? So I've now looked into the left subtree of F. Now I need to look into the right subtree of F. What would be printed after the B? If you have any suggestions, send it to the chat. Got the right answer. It's H, because from F, I'm going into G, I'm going into I, I'm going into H. H has no children, so I'm printing H. Then I'm going back to I. There's no right child for I, so nothing to do, so I'm printing I. And then I'm going back to G. For G, there was no left child, so I've done the right subtree. And then I'm printing G. And eventually, my F, which was the very last one. So now you've seen level order, in order, pre-order, and post-order. Level order is definitely the simplest one to run here, at least on the piece of paper. And in order, pre-order, post-order look a bit more complex. I know that. What we will try now is, we will try to implement this. So I'm going back to our code. Screen share will come very soon. So just going back to this code. So what we need is, I want to implement, say, in order. And I'm just calling this print. So print would be doing in order. What do you think, without looking at the slides, how much code we would need approximately for in order? Because we've just run it on a piece of paper. If you have any guess how many lines I need now to implement my in order, tell me. Got a right estimate, 5. So I need to check if there is something in the left. If there is something in the left, I need to do something. Then I'm printing my data. And then I need to check if something is in the right, and I need to do something. And what do I need to do here in self, if there is a left node? What do I need to run? Maybe you have any suggestions of the code I need to write. It's only one line of code. If you see something, maybe raise your hand or send it to the chat. And I'll do it. I'm doing it. We got a suggestion that is almost correct. Someone suggested I should do print self.left, but this would print the reference of self.left, but it wouldn't lead to the recursive call. So I need to say self.left.print. And then this in order, it's also recursive, would be called on the left subtree. And then we are printing the actual value. So we only have one proper printing on the command line here, because this one needs to be recursively in left. And so we need to do recursively in the right. And this is in order. Now, would it be easy for you to change in order to pre-order and post-order? If you think this, you see how to do this, maybe thumbs up if you, or green reaction if you don't see how to change this in-order implementation to pre or post-order, maybe red reaction. So please send some responses. Like green, it would be very easy for you to change this to pre-order or post-order, or red, you just don't see what I want to do. And there are currently no reactions, so I'd like to see a few reactions. Good, we got a positive reaction. Maybe you want to share with us what you would do in order to change this to a pre-order. You can also turn on your mic and tell us. So for post order, we would just move the print statement to the end. So we first do left, then right, and then print. And the pre-order, we just move this to the very top. So we just move this print statement either to the top for pre-order or to the bottom for post order, or in between the two ifs, and it's an in order. Now, we've done this before on the whiteboard. And now we actually want a computer to do this. So I'm creating now our tree from before. I want exactly the tree I had visualized. So I'm making a root node with entries with entry F. And now I need to add a left child and a right child. Obviously, I could say now root.insert B, for example, and root.insert G. We could build it step by step if we wished, but we can actually build this faster. So we can go through a string, which is BADCEGIH, which will just speed up building this tree. And I'm inserting this entry V. So this is a string. And if I iterate over a string, in the first iteration, V will be the first character, then the next character, and so forth. And I'm inserting a B, which would be the left node of F. Then I'm inserting an A, which is the left node of B. Then a D, it's the right node of B, and so forth. So it's just in the right order. If you change this order, you're still creating a tree, but not necessarily the tree I wanted from before. But we're inserting this now. And we can play with this now. We can say find value. I want to find out if there's an F. It's the root. An A is also in. An X is not in because we have not added an X. But we can now do our in order. So we can say root.print, and we're just printing in order. And there is unfortunately something wrong. Fix it. I had a typo here. It must be self. In the slides, it's obviously correct, but it's a live coding session, so it not necessarily always works the way we want this. So I'm just going back here in my history. So, and just so now I have my root again, and hopefully this time it works, but that's the fun of live coding, and not always works. So so now we are printing it, and we are printing it in alphabetical order, A, B, C, D, E, F, G, H, I, just the way we did it before. So I only had a minor issue when I typed it before. I typed right.right, which is obviously wrong, must be self.right, which I also intended to do. And if there is something in the right, I'm calling this recursively on the right. And your task is to re-implement this on your own, but you can also find this code in the resources file, and you can just move this print statement up and down for pre-order and post-order. So this is at least a very simple tree. What I've said is you can change the order of this here. You can, if you wish. You can just say you're at an A first or an H first. This will still create you a tree, but the tree may look different because based on the order, how we add something, it creates a different tree. And it can happen that we maybe have more elements in the left subtree or more in the right subtree. This is something about balancing the tree. It's a concept we will see later today. But you can also investigate this. You can change this order, and you can do the in order, the pre-order, and post-order and see how changing this order would influence the tree. And you can also try to look into the tree with the references and investigate it. When we introduced the abstract data type, I talked about generating and iterating. It's maybe a concept you're remembering, and this is something we will discuss in greater detail now, because I promised you we would discuss generating and iterating. So this is now Python specific, but this concept also exists in other programming languages. It looks slightly differently. In our terminology, an iterator is an object that allows us to iterate through a series of values. We've mentioned this term iteration before, like when we had an intro to Python and we iterated over all the elements of a list, for which we just used a loop or something. But we will now extend this understanding by looking at iterators and then at generators. So if I have a list and I want to go through the list, maybe I not only want to go through the list as one user, but as a second user. So I would need two links sort of to the list on how to go through it and how to manage the iteration. And for this, I need iterators. And I'll soon turn this into code and you will see it. So an iterator I is an iterator object. And that one points initially to the first element of the structure we want to iterate on. For example, a list or a tree, whatever. And then I can call next on that iterator, and it would return me the first element and move to the next element. When I call next again, I'm getting the next element, and so forth. And eventually this would be done and return a stop iteration exception when I have finished iterating over my structure. So the structure can be a list, can be a tree. We will discuss this soon and turn it into code. But somehow, so with next is built in Python, and I can call it on an iterator to get the value and then move to the next one. And I need to be able to create these iterators, and for this I need the iter built-in keyword of Python. And for some object, it creates me an iterator on that object. And I am able to create multiple iterators for the same object at a time. And this is something we start directly turning into code. So imagine I have a list. So L is a list, which are values for, well, we sort them. 1, 2, 3, 4, 5, 6. And I can have iterator 1, which is an iterator on my list. And then I can call next on I1, which would be the first value. 1, then 2, then 3. But I can in parallel create a second iterator on L, I2. So remember, running next on I1 has returned a 3. And if I call this again on I1, it returns a 4. But I can also call next on the second iterator, which starts with the first element, then the second element. So I can have multiple iterators pointing to the same object, but to different elements at a time. And I can just continue this. So I'm continuing with iterator 2, element 6, it's the last element. And if I call the iterator again, I get my stop iteration. And it turns out when you write a loop like this, for value in L, and something like print the value, internally, this for each loop creates for you automatically, so it's under the hood, an iterator on L, and each iteration of the loop, it calls next on the iterator again, assigns that value to val. So this is just some abstraction, and internally, this for each loop creates an iterator for you and stops when the stop iteration is created. But we've just done this manually by creating the iterator and calling next over and over again. And this concept of iterators is now important to trees, but we will also need it for hash tables in one of the next lectures. And we've used the concept already for quite a while without explicitly knowing what the for each loop does. But when we had the intro to Python, I also provided you with a few further readings and asked you to read a few things. And in fact, there was also a subsection on iterators. Maybe you read this a few weeks ago, maybe not. But that's why we're doing this now. Then there is another concept. Somehow the iterator needs to get its values from something. It can get it from a list, but imagine now you want to have infinitely many integers. You want to start with integer 1, 2, 3, and so forth. And you want to have a super long list. You could build this list up front, but it would be a very, very large list. And then it would take you a long time to build it up front. And you're unable to build an infinitely long list. So what you would rather want, rather than creating this list up front, is something you would want a generator. And the generator would not create you the whole list, but the generator would create the next value from that list. And then your iterator, each time your iterator needs a new value, the generator just creates that next value. And we will soon see how to build our own generator doing this. And all of you have been using a generator for a very long time since we started with this Python course. Do you know which generator you have been using all the time to get integers? If you have a clue which generator you have been using, tell me. We already got that answer. It's the range. Remember, so we had something like this, a range of 5. And then you want to see what's in R. You only see it's a range from 0 to 5, where 0 is included and 5 is excluded. In fact, this range is not a list. You can turn it into a list by calling list on R. So you're converting R, which is a generator, into a list. So you're getting all the elements. But if the range was super huge or even infinite, then this would take super long or never finish. And it's actually in Python 2, so we're using Python 3, but in Python 2, range was actually a list, not a generator. Now in Python 3, this is a generator, which is very helpful because if I have a huge range, I don't want to create a whole list up front. And I'll show you now how you can build your own range. In fact, we need to build our own generator. And we can say this generator is called first n, the first n entries. And it starts with 0. And we want to continue while num is less than n. So n is an upper boundary that is excluded. And I need to add 1 on top of num, but somehow I also need to return that value. And I'm not using a return statement because with a return, the method is done, but rather I use a statement in Python that is called yield. And yield works the following. So we have now a generator, and when I have an iterator on the generator, then I call next, and the code runs up to the yield statement and returns that value to the iterator or delivers that value to the iterator. And when I call next again, the code keeps running until the next yield statement appears. And we can test this now. Say we have an iterator I1 and we iterate on first n for value 10. So we can say we have an iterator for the generator first n where I passed 10 as my n, next value. First one is 0, then a 1, then a 2, and so forth. And I can have even a second generator. So I2 is my next generator. And it's a separate, I2 is not a generator, I2 is an iterator. And as we see, it runs independently from I1. So we have an iterator for that generator. You can always convert this into a list if you wish. You could just say, as before, like the list of the range, you can say we have a list of the first n. And when you pass first n with 10 to list internally, this would be run in Python until the iterator finishes. And in this case, we would then get a list. But this is something you would do quite rarely in Python, that you take the generator and extract all the elements, because it could be very large. And maybe it's not just integers, maybe it's some other kind of objects. So this could actually be then quite big, or maybe your generator is even unbounded and keeps running forever. And then turning it into a list will also never finish. So the beauty of the generator is you don't need to have all the values up front. Rather, you need a rule how to get the next value. And then you always request the next value as it's needed. And you don't need to pre-compute or waste memory. This is integrated very well into the Python language. In some other programming languages, this also exists, but in others, it's not integrated in the syntax, and building this is way more complicated. But that's the beauty of Python, that this is integrated here. Now, I'll switch back to the slides. You can remember we built this one here before. What we built here was the in order, the print method of our tree. But it's not a generator. All it does is it keeps printing and printing. Rather than printing, we could also have some mechanism maybe to store these values in a list. But actually, we don't want this. We don't want all the values of the tree up front. Maybe the tree is very big. Actually, I only want the next entry. So what I need to do is I need to take my print method from before and turn it into a generator. And this is something I will show you now. So what we have here is the print method, which did in order printing. But I want to turn it into a generator. So the first thing I should do is I would need to, rather than the print statement, I need to put in a yield. And the yield is the key of our generator. But it turns out that when I have such a recursive call on the generator itself, this one here and this one needs to be rewritten. And I'll show you how to do this. What we need to do is, and we don't call this print anymore, so allow me to rename this to in order, because we're not printing, we're doing an in order traversal. So I would need to say here, this is in order and in order there as well. But it's still a little bit of more code I need to do, because this generator, or this is a generator itself, and I cannot do it like this in Python, but this is just Python specific. So I need to go through each value coming from the recursive generator, and that element itself needs to be yielded as well. And I need to do the same down here for value in self.write.inOrder, and we yield that value. We will see very soon that with a newer Python version, we can improve this a little bit, but that's something we will see in a moment. It's just a minor improvement that we can still do here to make this a little bit shorter, but it doesn't matter for now. So we said we are creating our tree again. So we said the root is a node where we have an F. And then for, well, search just for V in, we are storing this in our tree. So I'm sorry about this with the focus. So I've just done before, I've created the root node, and I've added the elements. Now let's do the in order, but in order is now a generator. So we need an iterator on that generator. So the iterator is an iterator on our root dot in order. And then let's see the next element. The first element is an A, then a B, and we're not printing it, but the generator delivers it to us. So we could store it, we could print it, we could process it, and so forth. So we're not printing them up front, but we always request the next element. The tree may be big, and we may only need the next element and not all of them up front. So this is the beauty of these generators. There is a concept in Python that is called generator delegation. So one small issue, or it works perfectly fine. And this is something exactly the way one would have done it in Python until a few years ago. But you see, we have this for loop on the recursive call of the generator and then a yield there again. And there is now, since Python 3.3, a concept that is called generator delegation. And what it does is, rather than doing a loop on the generator recursive call and then yielding, I can say yield from this. But this is only a Python detail. So this is something that is not that important in this course, because it's not a Python course, but it just makes our code a little bit simpler because we yield from the recursive call. If you test it, it works exactly the same as before. It's just something available since Python 3.3. And that concept, I think, did not exist yet when the Goodrich book was published, because the Goodrich book is from a few years back. And that concept did not exist. And that's why I've added it here to the slides. So we yield from another generator. And this looks much nicer than having the loop here and yielding in the loop. So all the code is also in the slides, and the concept of so-called generator delegation, the yield from, is also mentioned there, and how to improve the in order. But these are just a few Python details, but what you should get from today is the concept of an iterator, the concept of a generator, and you can generate, and that has a huge advantage, and it's now part of the Python ecosystem, even with the range. That range is not a list, but a generator, which makes it much more usable than in the old Python version 2. A few more notes on trees for today, because we have a couple of minutes left. There is coursework on what we have just done. So there is the coursework problem section 12. This is the implementation we have done with the generated delegations, or just the version I have implemented. And your task is to also introduce a pre-order and post-order. So we have an in-order generator, we have an in-order printer, and your task is to turn both into pre and post order. But in fact, all you have to do is move the print statement or that yield statement up or down to get pre or post order. So this is fairly simple, but you should spend enough time on understanding these concepts and implement it on your own and test it, break it, get some experience. I think this would certainly help you to understand these tree concepts. There is a few more problems I want to discuss with you for the last 15 minutes or so. Imagine we have a tree like this, a tree that has a node, a root, a 4. The 4 has a 2 and a 7 as children, and the 2 has a 1 and a 3, and the 7 has a 6 and 9. And we want to invert the tree. Inverting means we are flipping the left and right child. So 7 would become the left child and 2 the right child. And in the children, we would also flip. So the 7 would go left, and for the 7 that move, 6 and 9 also get flipped, and 1 and 3. So an inversion of the tree would be the right subtree would become the left subtree, but also the children get flipped. So we do this recursively. What do you think, how much code this would be approximately if you try to implement this in Python? Any guesses here in the chat how much code you would need to implement an inversion of a tree? Like to see some guesses in the chat. Because you know how to build trees. We have a left and a right child. We store values in there. And now what I want is a new method to invert. Please send some guesses to the chat how much code it could take to flip or to invert. One person guesses 10 lines of code. Do you think 10 is good? If so, if you agree with around 10, thumbs up. If you disagree, maybe thumbs down, or green or red. I'd like to see if you agree with your fellow students. And there are only agreements. And it's true, you can do this in about 10 lines of code. And this is actually your problem 12.2. If you use recursion, your code will be 10 lines or even less than 10, depending on how you implement it. And what we want is a new function invert. So not a method, but a global function to which I pass a root node, and it would manipulate the tree that is represented by the root node by flipping left and right, if there is left and right, and then continuing this in left and right if there are left and right children, and you would stop at the leaves. It turns out, if it looks easy to you, it's not easy to others. Max Howell is a very famous person in computer science because he wrote Homebrew. Who of you uses Homebrew or knows Homebrew? Let us know. One person uses. So Homebrew is a package manager for Mac OS. So they're very good package managers for Linux systems. If you use Windows, you're probably not familiar with the concept of package managers, but they allow you to install software and dependencies and update them. And this is something that did not exist in Mac OS initially, or not very well. So Max Howell implemented Homebrew to add such a feature to Mac OS. And he was interviewing for a job at Google 10 years ago, pretty much 10 years ago. And when you apply at Google for a job, you are often tasked with supposedly simple algorithm problems. I know some of my friends, they work at Google, and the interviews I've been told is often it's about foundations of computer science. because Google believes if you know the foundations of algorithms and data structures and computer science well, then you'd be very smart and you would be able to manage all those more complicated tasks as well. This is something that has been criticized, but Google does lots of statistics and analysis on their hiring, and they believe to do it this way. If you're strong in foundations, you could be a good hire, and everything else could be something you can adopt to. So if you want to interview for a job at Google, maybe do this as quickly as possible once you have finished the algorithms and data structures class. Because if you apply for a job at Google in 5 years, maybe you forgot some of these foundations. And Max Howell applied for a job, and he claims 90% of the Google engineers use Homebrew because Mac OS is very popular at Google. But he was asked to invert a binary tree, and he just didn't know how to implement this. And he was on a whiteboard, and he was not hired then by Google, and he complained about this. So this has been very controversial. Some people claim, yes, you would not need in reality how to know how to invert a tree. That's too basic. You would be working on more sophisticated stuff. But others argue if you don't know the foundations, how could you do the more sophisticated stuff? So take a look at his link, at his Twitter post, if it still exists. But this is something that spread a lot on the internet 10 years ago. You can do this. With the knowledge we have done, you just need to flip left and right and continue doing this in left and right if there is a left and right. But if there's a non-reference to left, don't continue doing this in the left. Same for the right. That's why since this could have landed Max Howell a job at Google, I felt we could put this into their coursework. And it's just less than 10 lines of code. It's fairly easy. In reality, if you want to use trees in your code, use a professional Python library. Don't build trees always from scratch. It's something we're doing here to learn it. But if you need professional tree libraries, there's, for example, in Python, AnyTree, but there are others as well. So you can use trees with lots of features, maybe also for plotting the trees, checking dependencies, and other things. Feel free to look into AnyTree. Now, it turns out there is more than our binary trees. And this is something we will discuss next week in the lecture. So what you can do for today is you can do the coursework problem 12.1 and 12.2. You can also do 12.3. 12.3, we represent a tree as a list. And each entry in the list is a child. So what we have here is a list, and I'm just zooming in a bit more. And all the elements in the list would be the children of the root, because a tree can have more than 2 children. Next week, we will see such trees in which a tree has more than 2 children. And here we have this big outer list. And we have one child, which is a sublist, only a 1. The next child is a sublist with 2 elements. The next is a more complicated sublist where we have 4 but more sublists. So we see this list has 3 children. One child is this 1, the next child is this 2, 3 list, and all this other more nested sublist is the 3rd child. And you are asked to flatten the tree. So you would flatten the tree. You need to imagine you just squash the tree on the floor and all the leaves fall apart and they're just in the right order as they were in this tree structure. And you are asked to implement a function flatten to which we pass a node, the root node, which represents the tree, and it would return a list of this tree being flattened. Again, you can implement this in less than 10 lines of code if you know how to do it. My advice is make sure you use a generator to do this. And at one point, you will need a yield expression. And at one point, where these children have more subchildren, you need a generator delegation, a yield from expression. So this is something, if you understand the concept of generators and generator delegation, this will, again, take you less than 10 lines of code to implement. Next week, we will look at balanced search trees, which are an extension of trees, because I told you trees can be used to store data efficiently and to query the data efficiently. And for this, we need to add a little bit more theory, and we will see these balanced search trees. And then we will implement also decision trees, and we will do machine learning. A few things about the organization next week. Next week is a very nice day for the university, but a difficult day for our teaching, because next week, Friday, is the open day, which is in the afternoon. But as of 8 p.m., the department needs our lab room to prepare it for the open day. You are more than encouraged to go to the open day, because there will be lots of booths and a lot of stuff to see what's happening here on campus. But our lab room is not available at all during that day. But we won't be able to do our lecture in the afternoon, because in the afternoon there's the open day. And since there are no labs possible, we will meet next week, Friday at 8, and we will do a lecture from 8 to 11. And we will do it via Zoom and record it. And if you can attend it live, that's perfect. If you cannot attend it live, you watch the recording. And in 2 weeks, we are back on campus with 4 lab sessions and then the lecture in the late afternoon. And I hope you enjoy the open day. The reason we are doing this double lecture is the following. In June, there will be 2 lecture-free days university-wide, which are June the 6th and June the 20th. And there was already, and we have this open day. So because we have these 2 lecture-free days, June the 6th and June the 20th, they're not my invention. They're university-wide lecture-free days, have to do also with the public holidays in that period. We need to make sure we can finish the content of this lecture, because in this term we have 16 Fridays, but we only have but we have these 3 public holidays. There was one already recently. We have this open day, and last week I was on my business trip. So from these 16 Fridays, we actually have 5 Fridays left. 5 Fridays less, 3 for public holidays, 1 for the open day, and 1 for my business trip. That would mean we only have 11 Fridays for lectures, including the preparation for the exam. And that's unfortunately not enough to finish the content. And I want to make sure you learn enough in this course. And if this course was, for example, taught on Wednesdays, then we wouldn't have all these public holidays. But even if the course is on Fridays, I want to make sure we're able to finish the content. And that's why next week, Friday morning, we're doing the double lecture, just to make sure we also finish the content early enough. And that towards end of June, early July, we also still have a chance to do a practice session for the exam, which wouldn't be possible if we have all these Fridays where we are unable to meet. And on these 2 Fridays in June, June the 6th and 20th, there will not be labs, there will not be double lectures, whatever. So that will really be off for you. And that's why next week, Friday, we need to do the double lecture. And then as of 11, you can go to all these celebrations and events. Are you okay with that setting? Did you get it? Maybe just thumbs up or thumbs down if the setting makes sense to you. And with there not being any questions, I only see approvals. I wish you a great weekend, and I'll see you online next week, Friday. Take care and goodbye.